use the TXY diagram as a guideline. So by this time, week 3, you should know what the TXY diagram is, how to draw, and use the TXY diagram as a guideline. And then with okay, what's this TXY line? Let's draw this. So T x comma y, it should look something like that for ideal system. Yeah, using this diagram as a guideline, what I ask you with respect to feed plate, see figure below. Okay, I forgot to copy paste the figure, but I can draw it for you. In the distillation column, the value of Q that can be defined as the ratio of h suffix v minus h suffix f to h suffix v minus h suffix l dash. So there is l dash here. So discuss the effect of a feed enthalpy on the value of Q. So depending on enthalpy of your feed stream, how this Q value is going to change for the following feed conditions, which is feed is a saturated vapor, feed is saturated liquid, partly vapor, partly liquid, and feed is a liquid and at a temperature well below the boiling point, and finally feed is a superheated vapor. So for 5 different conditions, you have to tell me how the Q value is going to change. So before that, okay, obviously I will explain this during lecture hours what is a Q, but I'm going to derive the Q here because it's one of the most toughest topic in distillation. So it's worth to do it twice, one time during the lectures and one time during the tutorial as part of this question 4. So obviously for to answer question 4, you don't have to derive the Q, but I'm going to show it just to so that you will get a better picture about what Q is about. So typically for chemical engineers, Q commonly refer to heat flow. So in other modules, you must have learned this MCP delta T. That's something referred to as Q. But for distillation, for historical reasons, Q is referred to something else. So that's something related to the percentage of liquid in the feed. Yeah? So you can get Q in two different ways. One is by performing the mass balance over the feed plate in the distillation column, or by performing the energy balance over the feed plate in the distillation column. So for the question what we have here, we have Q is defined as the ratio of h suffix v divided by h minus h suffix f, h suffix v minus hl cap. So this is something related to enthalpy of a saturated vapor, enthalpy of feed stream, enthalpy of saturated vapor, and this is enthalpy of something related to the enthalpy of the saturated liquid. Yeah, so we have some conditions. We defined already Q, and we all I ask you to tell me what's the Q value will look like. Q will look like as a function of feed conditions. You know? So and historically in Q in distillation refers to, I already said it's something refers to the percentage of the liquid in the feed, and this is something we can derive using mass balance and energy balance. So let's derive it. Why not? Yeah? So I'll go through this topic slightly bit slowly because it's not an easy topic to understand. Okay, so let's do the material balance. The material balance is very simple. So for that, let's draw the. We don't have to draw the full distillation column because we are worried only about the feed plate at the moment. So this is the column and that's the feed plate, and let's say F enters flow rate. X suffix F is this is something you should know by this time, the molar molar concentration of the more volatile component in the feed, and then we also define the enthalpy of the feed, which is H suffix F, and then liquid that enters the feed stream we will call it as L, liquid that leaves the feed stream feed plate as L cap, and the vapor that enters the feed plate as V dash, and the vapor that leaves the feed plate as V. Okay, so these are just labeling at the moment. So let's perform a mass balance over the feed plate. So mass balance is very easy, am I right? In is equal to out. So what's in? F is in plus L, liquid that enters the feed plate, and then plus vapor that enters the feed plate. That should be equal to vapor that leaves the feed plate plus liquid that leaves the feed plate. Okay, and then we can so we are just doing the overall component balance, overall balance, not the component balance. So this is simple. So what we can do, we can rewrite f, we keep f on one side and we move everything to the other side. V dash plus L dash minus L minus V dash, and f is equal to, we can write something, I think I did some mistake, FL dash V out is equal to, there is no cap here. Okay, so let's erase this. Let me rewrite this, V plus L cap. Okay, so that looks correct to me. So let's strike this equation. So f is equal to V plus L dash minus L minus V dash. Okay, so I don't know how to say this. Whenever I say V dash, that means V, and then you put a dash on the top. Okay, and then L dash means L, and then you put a dash on the top. There may be a better way to express this, but I feel comfortable to say V dash and L dash. Okay, so we can rewrite this equation. So V minus V dash, and then plus L dash minus L. Okay, so and then if I divide both sides by f, this will become 1 is equal to L dash minus L divided by f plus V minus V dash divided by f, and then traditionally we call this term as f in the distillation. Okay, so this is only when we are talking about distillation, Q is defined as something like this, L dash minus L divided by f. So Q is equal to L dash minus L divided by f. So this is something about the liquid that enters, liquid that leaves, and the feed plate. So that's how we define Q. Okay, so how do you rewrite this equation? So we can rewrite this equation in a much more simpler fashion. So 1 is equal to Q plus V minus V dash by F, or Q is equal to 1 minus V minus V dash by F. Or we can even write in other way, 1 minus Q, you move the F to the left hand side, F, that should be equal to V minus V dash. So now we know what is Q with respect to distillation column. So Q is something related to the feed conditions. L is something related to the liquid that leaves the feed column, feed tray, which is L dash, and the liquid that enters the feed tray, which is L divided by F. F is the feed that enters the feed tray. Okay, so this is one way to get the Q value. So, and we can show that Q is something related to feed enthalpy. We can prove that this Q, which we obtained from a mass balance by performing a mass balance over the feed plate, this Q is a function of the feed enthalpy. How to prove that? To prove that, since we have the name enthalpy, we have to perform an energy balance over the feed plate. So let me do that. So pay some serious attention, because it's a very tough topic. This is so let's draw the diagram again. So let's draw the feed plate. So we have a feed plate here. So F is the feed, XF is the mole fraction of the more volatile component in the feed, and then the enthalpy of the stream is HF. So enthalpy, if you don't want uh, or if you want to understand it in a much simpler language, so enthalpy is something you can think it of as like a quantity of a heat a stream that carries. So it can exchange the heat with other stream, provided you give a contact and the time. sufficient time. So for the moment, enthalpy is something like the quantity of the heat carried by the material stream. Okay, if the material stream is at a higher temperature, it carries more enthalpy. And then if you already heat some liquid and then you convert it into vapor, then that vapor will carry even is at a very higher enthalpy than the liquid itself. Yeah. So and if you heat the vapor to something like a superheated vapor, then the enthalpy of the superheated vapor contains more amount of heat. So then obviously the enthalpy of the superheated vapor will be much higher when you compare to the liquid or when you compare it to the superheated vapor. Okay, sorry, saturated vapor. So let's come back to this topic. So let's define. So L and then the corresponding mole fraction XL, and then the corresponding enthalpy is H suffix L, and the liquid that leaves the vapor plate is L dash, feed plate is L dash, and then the corresponding mole fraction is X suffix L dash, and then HL dash. Okay, so that's the enthalpy of the liquid stream that leaves the feed plate, and then the vapor stream that enters the feed plate is V dash, and the corresponding mole fraction is YL dash, and then the enthalpy is YV dash, sorry, and the enthalpy is HV dash. And the enthalpy of the vapor stream that leaves the feed plate is just V, and then the mole fraction is X suffix V, mole fraction of the more volatile component. Oh, sorry, this is Y suffix V. Whenever we talk about vapor, we use the notation Y, and then the enthalpy of the corresponding stream is H suffix V. Okay, and what's given in the question is we have something in the question which is the function of this V and L dash. So let me write in the question we have Q is defined as what. Let's go back to the question. So Q is HV minus HF, yeah? HV minus HF, H suffix V minus HF divided by HV minus HL dash. Okay, so this is what something which is given in the question paper. So we can prove this. That's what we are trying to prove now. So to do that, we have to perform an energy balance. So let's do that. So energy balance is simple. Energy in equal to energy out, which means energy is conserved around the feed plate. Okay, so no energy loss around the feed plate. And then another assumption, which is a reasonable assumption and can be proven experimentally, is that the enthalpy of the stream that the liquid that enters the feed plate and the liquid that leaves the feed plate are almost similar. You know, so they are very close. So it is reasonable to assume the quantity of the heat that this stream can carries and this stream that the stream that leaves the feed plate is almost similar. You know? So that's we can assume HL is equal to HL dash, and then similarly HV equal to HV dash. So we are assuming that enthalpy of the both streams are similar, okay, or same. So that's why we are making some assumptions like that. And now let's do the mass the energy balance. So energy balance is simple. So before doing energy balance, let's write the overall balance just for our convenience. So we can use this as a guideline to perform the energy balance. So what's this? So this is something in and this is out. So we can do the energy balance. So how much energy each of this stream carries. You know? So that's something we can do. FHF plus L multiplied by H suffix L plus V dash multiplied by H suffix V dash. So that's the enthalpy of the stream V dash equal to V multiplied by H suffix V plus L dash multiplied by H suffix L dash. Okay, so let's write everything. So let's keep FHF in one side and then we put everything on the other hand side. So FHF is equal to VHV plus L dash HL dash minus LHL plus V dash H suffix V dash. So and then we can simplify this equation. So something like V minus V dash into HV minus, so this is something we can do because we assumed HV is equal to HV dash, okay, minus, or we can put plus we have L dash minus L into H L dash, okay. So this is something we can write because we assume HL dash is equal to HL, which is a reasonable assumption, to be honest. And then F HF. So let's divide both sides by, oh, no, we don't have to divide. Let's plug in the something that we already obtained from the mass balance equation. So from the mass balance equation we obtained what? We obtained Q is equal to L dash minus L by F, you know, L dash. And then we also know that 1 minus Q into F, that's equal to V minus V dash, okay. So plug in these values here. So for V minus V dash, substitute 1 minus Q multiplied by F. For L minus L dash, substitute QF, okay. So let's do that. FHF is equal to 1 minus Q F H multiplied by V plus, this is QF multiplied by HL dash, okay. So we're going to get a much more simpler version for Q from the energy balance expression. So we have FHF, expand, I'm just expanding the equation, X suffix V minus QF H suffix V plus QF HL dash, okay. So we have F throughout the expression. So this is, if you divide by F on both sides, so you get something like by F by F by F by F. We can get a simpler version, HF equal to H suffix V minus Q H suffix V plus Q into HL dash, okay. So always remember that enthalpy is something like the quantity of the heat that you carry, okay, or the quantity of the heat it is generated if there is a chemical reaction, you know? So something related to the quantity of the heat, yeah, not the temperature itself. So HF minus HV is equal to Q HL dash minus HV, or Q is equal to HF minus HV divided by HL dash minus HV, okay. So if you multiply this equation, for example, if you multiply and divide this equation by minus 1 in the numerator and the minus 1 in the denominator, we get something which is given in the question paper, which is HV minus HF divided by HV minus HL dash, okay. So Q, the traditional Q with that corresponds to the Q in the distillation, you know, related to the topic of distillation, okay. And we are going to prove that. So that we are going to answer the question, which is, we have to prove that this Q is a function of the feed enthalpy, okay. So this is something we have to prove. Let me prove that. So before that I will give you some easy things, or easy method to remember a few things, yeah? Okay, it's not even a method, it's a okay scientific concept. So how to do that? What do we mean by that? So draw the TXY diagram, put T on the y-axis, X comma Y, draw the diagram, okay. Before that let me explain this Q. So QHV, this is something related to H of saturated vapor. HF is related to enthalpy of the feed stream. HV is related to the enthalpy of the saturated vapor. HL is related to the enthalpy of the saturated liquid, okay. So keep these things in the mind, and let's show few things here on the TXY diagram. So draw a tie line here. So this point is nothing but saturated vapor, so that should be equal to HV with respect to this tie line, and this point is saturated liquid. The enthalpy should be equal to HL dash, which should be equal to HL, and then somewhere in the midway, which is the two-phase mixture, which is partly liquid and partly vapor, so that point should be, so that head should be less than enthalpy of the vapor stream and should be greater than the enthalpy of the liquid stream, okay, or the saturated liquid, and this head should be less than the enthalpy of the saturated vapor. And somewhere in the top you have a superheated steam, or sorry, not steam, superheated vapor, sorry, so that should be, so enthalpy of the superheated vapor, so that should be greater than the enthalpy of the vapor, comma enthalpy of the saturated liquid, and else, okay. And you also have something here which is subcooled liquid. This is well below the boiling point of your more volatile component, so somewhere here that should be the enthalpy of the subcooled liquid. So this should be much smaller than the HL dash, okay. So we can arrange them in a particular order. So how do we write that? So enthalpy of the supercooled liquid, this is smaller than or lesser than enthalpy of the saturated liquid, okay, and this should be less than the enthalpy of the two-phase mixture, which is partly liquid and partly vapor, and this should be less than the enthalpy of the saturated vapor, and this should be less than the enthalpy of the superheated steam, superheated vapor. That is, we are not talking about steam. HV or HV dash, okay, as we assumed HV equal to HV dash, and we also assumed H suffix L is equal to HL dash, okay. So just by looking at the TXY diagram, you get an idea which quantities carries more which of these parameters carries more heat. So subcooled liquid carries less heat, and then saturated vapor carries heat which is slightly higher than the subcooled liquid, and this two-phase mixture point, this carries more heat when you compare to saturated liquid, and then the saturated vapor carries more heat when you compare to the saturated liquid, and the superheated vapor, it carries more heat when you compare to saturated vapor. Yes, so just by looking at the texture diagram you got some picture. Yes, so with this knowledge we can answer the question, which is what's the effect of feed enthalpy on the Q. Let's do it one by one. So let's start which is more convenient for me. Okay, so let's start with the saturated liquid. See, if the feed is saturated liquid, so in the TXY diagram, so saturated liquid is here and your saturated vapor is here. Yeah, so let's write Q is equal to HV minus HF divided by HV minus HL dash. So what I say is enthalpy of the feed is, if the feed is saturated liquid, so which mean HF should be equal to HL or HL dash, because that's the enthalpy of the saturated liquid, and we know that HL is less than HV. So this means, saturated liquid, we know that okay, forget this one, which one is greater than what. So then HF should be equal to HL or HL dash, so which mean HV minus HL dash divided by HV minus HL dash. So this is equal to what? Equal to 1, am I right? So if the feed is saturated liquid, Q is equal to 1. Let's solve the next part of the question. So what is that? If the feed is a saturated vapor, if the feed is a saturated vapor, very tricky question to be honest. So Q is equal to HV minus HF, HV minus HL dash. What I say is your feed stream is a saturated vapor, which means this one, which is equal to, which means HF should be equal to this enthalpy of the saturated vapor, or H suffix V or H V dash. Okay, so what's that mean? So this means HV minus HV divided by H suffix V minus HL cap. So this should be equal to 0. So what? If the feed is a saturated vapor, Q is equal to 0. So why are we studying this? This is something we have to study because later at some stage Q decides where your feed plate is. Okay. So that's the main reason that we are studying this. So depending on the Q, we are going to determine the slope of something called as the feed operating line. So we will come to that later, not now. Okay. And then what is this? Let's go to the next point. Maybe superheated vapor. This is easier to answer. Superheated vapor. So what is that? In the TXY, superheated vapor is somewhere here. Okay. And this is greater than HV. HV is your saturated vapor, which is somewhere in this side of the tie line. Okay. So definitely superheated vapor. If the feed stream is a superheated vapor, then HF is something greater than enthalpy of the enthalpy of the saturated vapor. In that case, Q is equal to HV minus HF divided by HV minus HL cap. So since HF is greater than HV, HV minus HF should be a negative quantity. Okay. And then if we divide it by, so vapor, this is a saturated vapor and saturated liquid. So in the tie line, saturated vapor is here, saturated liquid is somewhere around here, and we know HV dash is greater than HL dash, which means divided by a positive quantity. So this makes it a negative value. So when the feed is a superheated vapor, Q is negative. Okay. So let's go to next point. Okay, these are slightly difficult topics, so forgive me for making it a bit complex, but I try to make it a bit simpler. I'm trying to explain this as simple as possible, but I have to confess it's not an easy topic. So you need a really serious understanding about how temperature works, how the enthalpy works, and what actually enthalpy is. Enthalpy is just the quantity of the heat carried by something, or released during during a reaction or something. So enthalpy is something related to quantity, not temperature. Okay. Obviously it's related to temperature, but it's not directly, we cannot say that's equal to temperature. It's something related to the quantity of the heat that we are carrying. And then let's go to something else. So what we can do, so if the feed is well below the boiling point, this is another extreme case. So is well below the boiling point of say more volatile component. My handwriting is not good, but since I'm talking, you should know what I'm saying. So in the TXY diagram, sorry, it's not a great diagram, but you know how the TXY diagram looks like. Yes, this envelope should range from 0 to 1. Okay. The well below the boiling point of more volatile component, they say this is somewhere around here, this point. So this is a subcooled liquid, or let's call it supercooled liquid or subcooled liquid. And then see this enthalpy, if your feed is a supercooled liquid, then HF is definitely much lower than, say, draw a tie line here, is lower than the the saturated vapor, which is HV or HV dash. remember we assumed h suffix v is approximately equal to hv dash. Okay, so in that case, how to get more space here. Case, what we have in that case, so let's write q is equal to hv minus hf divided by hv minus hl dash. So in that case, for sure we know that hf is much smaller than the value will be uh, relatively smaller when you compare to hv. Yeah? So in that case, hf will be really smaller than the hv. So this means you get a positive quantity on the top, and we already know that enthalpy of the saturated vapor should be greater than enthalpy of the saturated liquid, so which is a positive here. So this is a positive quantity. So typically q will be greater than 1 if your feed liquid is well below the boiling point of the more volatile component. Okay, so let's go to fifth condition. What we have, let me check the question. Okay, one more condition that we have. So this is okay, what we have here. The last question is, if the feed is a two-phase stream, so partly liquid, partly vapor. So we are just playing the game using the txy diagram. Okay, so txy, saturated liquid is here, saturated vapor is here, two-phase mixture is somewhere around this point. So which means enthalpy of this particular point should be greater than the enthalpy of the saturated liquid and should be less than the enthalpy of the saturated vapor. So this means q, which is defined as hv minus hf divided by hv minus hl cap, this should be equal to positive quantity on the top divided by a positive quantity on the bottom. So q is again a positive quantity for a two-phase mixture if the feed is a two-phase mixture. Okay, so if you want we can make a summary. So the feed condition, so that's why I said q depends on the enthalpy of the feed. So q is purely a function of enthalpy of the feed with respect to distillation. So at the moment we are talking about distillation. Yeah, so q is not heat flow. For if you are discussing about distillation, q is something related to your feed condition. So from mass balance we know q is equal to L minus L dash by F. Yeah? So try to remember these things. I know it's tough, but once you learn or once you understand, then things will become easier. Sorry, this is L dash minus L. Okay, so q is L dash minus L by F. So depending on the feed conditions, so what's the q value? So let's rewrite. So let's summarize this. Yeah? If it's a saturated liquid, q is equal to 1. Saturated vapor, q is equal to 0. And then what we studied, condition 3. If it's a superheated vapor, then it's negative. Superheated vapor. It's negative. And it's a subcooled liquid. Positive. Typically q will be greater than 1. And if it's a two-phase mixture, which is partly liquid and partly vapor, again a positive quantity. Yeah, that's all for the moment. Let's go to the next question, which should be really easy. So use the diagram below to answer question blah blah blah. Yeah, I know we already answered it. What is this? Something appearing here. Let me erase that. How to erase it? Okay, let's go back to the problem. My god, what is this? It's not allowing me to select the pen for some reason. Okay, let's go to the pen. Okay, what's this? Okay, this is not correct. Your supercooled liquid will be typically well below the boiling point of your more volatile component. Yeah? So it should be somewhere around here. So that's the place for supercooled liquid. Okay, what I asked. Let me read the question again. Use the diagram below to answer the question above. Yeah, which is I already explained where things stands. So with saturated liquid is here, saturated vapor is around this point. Follow the pen. Two-phase mixture is inside the envelope. Subcooled or supercooled liquid is around here. Superheat vapor should be above the boiling point of the less volatile component, which is somewhere around here. Yeah. So based on that, we can explain how which point carries the more heat, the quantity of the heat, to be precise. And okay, this is something I think. Okay, I will delete this one. Actually, I recorded this video before, but for some reason there is no voice, so I'm re-recording it. That's why you are seeing some contents here. Let me delete it. What's this? Okay, I can redo it again anyway. Oh, what's this? Okay, construct a model TXY diagram. So this time follow the blue color pen. Okay, so construct a model TXY diagram for an ideal binary fluid mixture. Okay, it's a two-phase mixture, and this diagram indicate labeled the following points: something corresponding to saturated vapor, saturated liquid, two-phase region, point representing superheated steam, and pure liquid at a temperature well below the boiling point of the obviously the more volatile component. So we know how the TXY diagram works. This is I'm crying almost for 3 weeks now. Tx comma y. Yeah, so that's how it looks like. So your subcooled liquid somewhere around here, supercooled liquid, your superheated vapor is somewhere around here, and then you draw a tie line, one end of the tie line that cuts the y-axis, the ty line. So that's the superheated, sorry, saturated vapor. And then the tie line where it cuts the tx line, that's the saturated liquid, and anyway in between the tie line, that's the two-phase region. Okay, I think we almost completed the tutorial, all the questions in that we designed for tutorial 3. If you have any doubts, please do not hesitate to write me. So obviously, okay, as part of tutorial I did a lot of derivation. That's because this topic is really is complex, and it gets even more complex in the coming weeks. So if you know how the enthalpy and how the temperature works, then the distillation is very easy. So I will stop. I could add the derivation for the mass balance line for with respect to distillation column. Okay, maybe this is something we can focus next week, not this week. Yeah, thanks for listening.